class is finished. Can you hear us?
Yes, sir.
And can you see the board?
Yes, ma'am. But can you switch off the light just above the blackboard?
Is it better now?
Yes.
It's fine. All right, thanks. So 12:30, I'll stop it. Yeah, I just want to announce that I thought I'd take up to 1:30, but I'm actually going to take only up to 12:30 because you have your STQM class at 12:30. Okay. So let's go back to what I was doing last time. I was talking about the inertial tensor. So what we imagine is that we have rigid bodies, and for simplicity, what I assume is that I take this rigid body to be made of point particles, which are attached to say some origin which I have fixed, and this is at some position C. So the alpha particle is at position alpha. Okay. So this is like say 1. The first particle is at position R1. The second particle is there at position R2, and it has mass M2. It will have different masses, and then say the third particle is at some position labeled by R3, and it has mass M3, and this way so on. So I have a collection of n particles which are at positions R1, R2, Rn with respect to some particular origin, and what I wish to find out is, and this is a rigid collection of particles, so you can assign, you can imagine that these point particles are attached to the origin by some light rods. And then what I'm doing is, I'm taking this whole assembly of particles and I'm rotating it about some axis, which I will specify by the unit vector n. Because if I say I want to rotate about a certain axis, then all I need to specify is the direction. So that's why it's enough for me to specify the unit vector n cap. So unit vector n cap I can write like this. So this n1 cap, n2 cap, and n3 cap are the components of this unit vector along the I cap, j cap, and t cap directions. It's a unit vector, so dot product of this unit vector. So I rotate about this axis specified by the direction n cap, and by angular frequency is given by magnitude omega. So now I have this rigid assembly of particles and rotating the whole system by about the axis n cap by or the axis along the n cap direction by an angle omega. So you expect that this whole thing should have some angular momentum. So you want to find out what is the total angular momentum of this system of particles. And what we saw yesterday was that I can write down the total angular momentum in terms of the angular momentum for each of these individual particles. And what we saw yesterday is that I could write this whole thing in the following way. So formally I can write this as simply like, for each particle you're going to simply get R cross B. So I have R alpha cross M alpha V alpha. And then I do the summation. So this is the momentum, linear momentum. This is the position of the particle with respect to this origin. So remember, angular momentum, whenever I talk of angular momentum, it's always with respect to certain origin or a certain choice of the origin. Then I sum up for all of this. And then what you do is you use the fact that your V to the alpha particle can be simply written as so this is nothing but by definition it's dr alpha by dt. And when I have this kind of a rigid rotation, it's simply going to become omega cross. Okay. So when I define my omega vector to be the following, that is equal to omega times E. And then what we did was, so this particular thing now I will replace by, so I just recalling what we did yesterday. I will have this M alpha here, then I have R alpha cross this omega cross R alpha. And then by using our tensor, using the tensor algebra, what we saw was that I can define it an object. It is in this form. So I defined yesterday I alpha ij is equal to R alpha square delta ij minus of x alpha I x. And I also multiply with the name, so it's plus. So if I define this quantity I alpha for each particle, the alpha particle, if I define this quantity, now you can see that this quantity transforms like a scalar. A tensor of rank 2, a second rank tensor. Because this yesterday we saw already that this transforms like a second rank tensor, and all I've done is multiplied it with a scalar, so it still will transform like a second rank tensor. And then if I define now the sum of all this, so Mij I will define as sigma alpha equal to 1 to n. Then what you can see is that this whole thing can be written as Mij. Or in other words, or you have Li can be simply written as Mij. So again, you can see that the equation which we have written now for the angular momentum is in what is known as a covariant form. Because the left-hand side transforms like a vector or a tensor of rank 1. The right-hand side is a combination of two objects, one of which transforms like a vector because omega vector is omega n cap, and the other is like a tensor of rank 2. And what I've done is contracted this tensor of rank 2 with the tensor of rank 1, and I will end up then on the right-hand side with an object which again will transform like a tensor of rank 2. So this equation is, as I said, it's in a nice form, but it also says something more because it tells you how the system or how this assembly of particles are going to respond to a particular rotation. Because if I'm rotating about some axis n cap, and this omega j will be then omega times nj or nj cap. So it will tell me about how it responds, and the response will then depend upon this Mij or the coefficients Mij. Now Mij is a second rank tensor. It has 9 components, and from this we can let us say a little bit more about the properties of this object. So your Mij is a tensor of rank 2. Which is from definition here. What is Mji? Or let's go back here. If I, for the alpha particle, if I define this like this, what is Iji? That means what is, suppose I ask you what is Iji alpha. By definition, see, whenever you have such things, you just take the definition. So wherever the first index is, for the first index in this, just put j. For the second index, put I. So I get delta ji here. And here I'm going to get xj alpha, xi alpha. But you can see that this is the same thing as iij. So you can see that this is equal to iij alpha. So what kind of a tensor is this? If your iij is the same as iji.
Symmetric tensor.
It's a symmetric tensor. So obviously for each of these, for the alpha particle it is symmetric. Now I'm adding up for all the different alphas for the collection of n particles. So you can see that then Mij will be the same as Mj. So what we find therefore is that this is a symmetric tensor of rank. And this particular tensor M is called the inertia tensor. So the inertia tensor is a symmetric, is a rank 2 tensor, and which is symmetric. So how many independent components will it have actually? So if I write M, the matrix form of this, so it's going to have M11, M12, M13. What will be this object now? It is symmetric. This should be M21, right? But if it is symmetric, what should this be equal to?
M12.
M12.
It should be the same as M12. Similarly, you can see that this should be the same as M13. For the diagonal, I can't say anything. Then I will have here, I'm sorry, this should, yeah, so I put 1, 2 here. Then I will get 2, 3 here. But then this should be the same as this and this. So how many independent components does this have? You see, this is what I will is like. This is equal to M12. So that there's no confusion. Okay. So how many independent components it has? It has a diagonal elements which are independent, because I cannot say anything about these 3 and these. So although you have 9 elements in your matrix, in your tensor, finally you will actually get only 6 independent components because of the fact that it is symmetric. Further, you can see so let me put this somewhere. I'll put that relation Li equal to Mig omega t. Now, if your matrix N is this and it has the symmetric property, notice it's also something you can see from here that this quantity. Okay, so let's explicitly write down some of these quantities. Yeah, I would write it down. Okay, so here you have R square and here you have Xi, Xk. Now these are real elements. I mean, R square is a real quantity. It's in fact a positive quantity, but it's a real quantity. X are components of your position vector for the alpha particle. So that's also a real number. And you have multiplied it with this mass for the alpha particle. So this is again a real number. So basically the elements of Iij are real. So therefore your Mig has all real elements. So it's a symmetric tensor of rank 2 with real elements. All the elements are real. Now can you tell me what is M dagger? So now think of this as a matrix. Then by definition, what is M dagger? Given a matrix N. How do you define the dagger of a matrix?
Conjugate and transpose.
Pardon?
Conjugate and transpose. Complex
Yes.
conjugate and transpose.
So it's nothing but the transpose of the complex conjugate matrix. Right? But now my matrix is real. So your M star equal to M. So therefore this tells me that this is equal to M transpose. Okay. But if you have a symmetric matrix, what does this mean? What is M transpose? What is the relation between symmetric matrix and M? If I take the transpose of this, what will I get?
Equal. M transpose equals to M.
So because it is symmetric, this implies that M transpose is the same as M. So therefore I find that. So I find therefore that M dagger equal to M. So what kind of a matrix is this? If your M dagger is the same as the M, what kind of a matrix is it?
Unitary.
No. It's not unitary. That's some other name. Unitary is if M dagger equal to M inverse.
Hermitian. Hermitian.
Okay, so this tells you that M is a Hermitian matrix. So now what I'm going to do is, diagonalize this matrix. Okay. So again, I get like what I did with electrical conductivity tensor. I would like to diagonalize this matrix, because if I diagonalize, say if I go to the basis, you can see this relation I have. Suppose this was a diagonal matrix, then what you can see is that in that case I'm going to get, say for example, I only have L1 1, M2 2, M3 3. Then I'm simply going to get L1 equal to M1 1 times omega 1. L2 will be M2 2 times omega 2, L3 is equal to, or in other words, your angular momentum will be parallel to the rotation, to the omega vector, to the angular frequency vector. In that case, okay. So I would like to diagonalize, but again, when I want to diagonalize a matrix, what do you do? We already discussed this yesterday. If I wish to diagonalize a matrix, what do I do?
Find out the eigenvalues.
Again, I solve the corresponding eigenvalue. So I want to solve this eigenvalue problem. So to diagonalize them, solve the eigenvalue. So I will get this particular thing. So I have to solve for the lambdas and I will get the corresponding eigenvectors. Now, how many eigenvalues will this have? It's a 3 by 3 matrix. So how many eigenvalues I will get? In general, altogether, how many eigenvalues I should get?
3.
So let lambda 1, lambda 2, lambda 3 be the eigenvalues. Now, before doing it, without doing any calculation, can I say something about what possible values this can be? Given that your matrix is Hermitian, what can I say about what should be the properties of these eigenvalues?
They should be real.
So I know that. So because M is Hermitian, you can see now how your vector spaces or matrix algebra helps you. It says that lambda I must be real. So without even doing any calculations, this much I can say. And if you get, when you finally do calculations, if you get some complex answer, then you know that you're wrong. That you have made some mistake in your calculation. Okay. Now, so given this, so now I have M to be a Hermitian matrix, and I suppose I solve the eigenvalue problem and I find these three eigenvalues and let the corresponding so let me write this. So let U1, U2, U3, or let's write it as phi 1. Yes. So let phi 1, phi 2, phi 3 be the corresponding. So I write it as phi here. So there's no confusion. Be the corresponding eigenvalues. Now suppose I have these three eigenvalues. So I have lambda 1, lambda 2, lambda 3. I already know that these must be real. Now suppose they are all distinct. That means lambda 1 is not the same as lambda 2. None, any of the two are not the same. Okay. So let's consider the case lambda. Okay, first let's just suppose this is that all the three eigenvalues are distinct eigenvalues. What can you say about these corresponding eigenvectors? Or maybe I'll remind you this way, that suppose you have a Hermitian matrix and let us say I got two eigenvalues for that matrix, lambda 1 and lambda 2. And let's say the corresponding eigenvectors are phi 1 and phi 2. And suppose your lambda 1 is not the same as lambda 2. What can you say about phi 1 and phi 2 eigenvectors?
They're linearly independent.
A little bit more than that? Yeah, okay, they are linearly independent. So So what would that mean then? You're right. I mean, they're linearly dependent. So what can I? What a little bit more than that? I would like to put it in a slightly different language. This tells me that phi 1, phi 2. So if I just take 2, for example, it will tell you that they're linearly dependent, or in other words, phi 1 and phi 2 are orthogonal to one another. Alright? And in this case now, if you have 3 distinct eigenvalues, then I will get 3 linearly independent eigenvectors, which are all orthogonal to each other. So it's actually a little bit more than this. So phi 1, phi 3 are mutually orthogonal. See, this simply follows from the theorem for Hermitian matrices. That if you have a Hermitian matrix, and if you have 2 distinct real eigenvalues, then the corresponding eigenvectors are orthogonal to one another. And remember that when we solve all of this, we are not solving for the trivial case, so these phi's are non-trivial, which means that they cannot be the zero. And so, which means if they are not the zero vector, I can normalize these. And let us say that, okay, so let me say that I have this combination now. So I normalize phi 1. So normalize phi s. Suppose I define now this phi I can to be equal to phi I divided by n. Then you can see that phi 1 cap, phi 2 cap is equal for I equal to 1 to 3. This will form an orthonormal basis for your 3-dimensional space. Right? So, in other words, what it show is that, all right. So if I take my, I'll give you some. This perhaps you people have done in mechanics. I'm not sure. If you've done it, fine. It's a repetition. Like they might give you a certain thing. If you have not done it, then I'm going to open this something you can do. Okay? So this mutually orthogonal, or this mutually perpendicular. Okay. So associated with M. So already we can associate with M. Three mutually perpendicular axis. Okay. And these axes are called as known as the principal axis of the inertia. Okay, I have shown you for the case when lambda 1, lambda 2, and lambda 3 are all distinct, but we will also see we can generalize this to even when they are not this, when there are more than one eigenvalue, or when if there are two of them which are the same, or even more than all three are also the same. I'll come back to that in just a minute. So by solving the eigenvalue problem, you know that you have, so you're essentially solving the eigenvalue problem for this Hermitian matrix M. So you know the eigenvalues are here. And associated with these 3 real eigenvalues, I will have the corresponding eigenvectors phi 1, phi 2, phi 3, and I can associate them with M three mutually perpendicular axes which are known as the principal axis for the this. Now, so if I made this transformation, so basically I started with this end, then I've gone to this diagonal form, which I will call as a diagonal. So the end diagonal form will be of this form. Lambda 1, 0, 0, 0, lambda 2, 0. Okay. So essentially what it means is that suppose this was my coordinate axis I started with I cap, j cap, k cap. Now so let's consider first the case I'm just taking when they are all distinct. So for the distinct I've already shown you that I can construct this set of orthonormal basis vectors. So I go now to a new set which is phi 1 cap, phi 2 cap, and phi 3 cap. So I can go to this new coordinate system, which is a new coordinate axis, which is described by the directions along phi 1 cap, phi 2 cap, and phi 3 cap. So the axes are along these three different directions. And so if I choose now, this is my new basis, that P prime is this. Then in that case, so I call this now as P prime. So my inertia tensor simply becomes this. Now in this basis, what does this equation become? You can see that in this basis, your L prime I will be simply equal to N prime Ig J. But since your M prime in this basis is simply this, so you can see that it's simply going to become, which implies then, for example, that L1 prime will be simply equal to lambda 1 omega 1 prime. L2 prime will be equal to lambda 2 omega 2 prime. And L3 prime will be equal to lambda 2. So that means if I go to this choice of coordinate axis, this phi 1 cap, phi 2 cap, phi 3 cap, or if I choose the principal axis of my inertial tensor as the three mutually perpendicular principal axis of my inertial tensor as the coordinate axis, then in that case the angular momentum and the angular frequency have this very simple relation. Or in other words, what you can see from here is that the angular momentum is simply parallel to your angular frequency. That means if I rotate, for example, so if I rotate my body about one of the principal axes, so if my omega prime is simply equal to say phi 1 cap omega 1, okay? I'll just call it like this. If this is equal to this, then what this tells me is that L1 prime is simply equal to lambda 1. And if it says L2 prime is 0, L3 prime is 0. So in other words, what it is telling me is that if I rotate, now I have, so again let me emphasize, I have this rigid body, I constructed the inertial tensor, and I'm assuming now for this case that I have three distinct eigenvalues for the inertial tensor, lambda 1, lambda 2, lambda 3. I found out the corresponding eigenvectors, and these must be mutually perpendicular, and which are I call as principal axis. And now I'm saying that suppose I take my rigid body and rotate it about one of the principal axes, say for example here, I'm rotating it about the principal axis phi 1 cap by some angle omega 1 prime, then what you can see is that then the angular momentum is only along that axis. And the value will depend, so it will depend upon the angular frequency and this lambda 1. So the diagonal element, this is called as the moment of inertia. So the diagonal elements of M are called as moments of inertia. And I think when you studied about moment of inertia in school, this is how you actually study. Okay, maybe we can help and just come back. So if I rotate it if I rotate my body about the phi2 axis, then in that case I'm going to get here A2. Only I will get an angular momentum along the phi2 direction. If I rotate about the phi3 axis, then I will get an angular momentum about the phi. But we also saw what is Mij. See, my Mij by definition was this: alpha equal to 1 to m alpha, and then I had this r alpha square delta Ij minus of x alpha I x alpha. So now let me say I've gone to that new basis A prime. So I simply am going to write this as A prime. Nothing will happen to this mass part because that's a scalar. This is simply going to become now prime here. And I'm going to get delta prime here, and prime. Okay. So I've gone to the new basis. But we know what the answer should be. Because in the new basis, this should be simply equal to lambda 1, 0, 0, lambda 2, 0, 0, lambda 3. Because that's how I've chosen my new basis. Fine. Or in other words, you can see from here, I'll just write down for the one particular one because I think I'll just write down for the ith alpha, for the alpha one, the inertia tensor. So if I write this explicitly, you can just look at this explicitly. This is going to be m alpha times. Let's write down the coefficients. Okay, this is r alpha. Before I do the transformation, that is, I'm just writing down without doing the usual basis. I have r alpha square. So this is like r square delta Ij minus of xi xj. I'll drop the alpha index this. Okay, so let's just look at the elements of my inertia tensor. Now for 1, 1. So before I go to the transform, okay, in the unprimed basis, in basis B, okay, it's going to look like this. R squared is what is R squared for the alpha particle? Or in general, what is R squared?
x1 square plus x2 square plus x3 square.
X1 square plus x2 square plus x3 square. Now I have m11 here. So, sorry, I1. I have 1, 1 element of this object. 1, 1 element. So if I take 1, 1 here, what will I get? I'll get delta 1, 1. So that answer will be 1. Fine. So if I take I equal to 1, j equal to 1, I'm going to get from this element r square. And then I'm going to get, because delta 1, 1 is 1, then I'm going to get minus of x1 square. So what will that be? This is going to be then x1 square plus x2 square plus x3 square minus of x1 square. Agree? So therefore, I'm simply going to get x2 square plus x3 square. So what you will see is that for this particular one, I'm going to get x2 alpha square. I'll drop the alpha index, okay, for the minute because that's simply confusing. So you will get x2 square plus x3 square. Now if I take the 1, 2 element, what will happen? This part is going to give me 0 because delta ij will be 0. And from here I'm going to get xi 1, I equal to 1, and this is 2. So I'm going to get minus of x1, x2. Similarly, this is going to give me minus x1, x2. And from symmetric matrix, so I can simply write down this as x1, x2 minus x1, x3. And from here now you can see when I take the total element, again this is going to give 1, 1. But now I'm going to subtract. Here I subtracted x1 square. Now I'm going to subtract x2 square. So I'm going to get here x1 square plus x2 square. Sorry, x1 square plus x3 square. Then here I'll get minus x2, x3. Then I will get here again minus x2, x3. And finally I'm going to get here x1 square plus x2 square. So for the alpha particle, this is your, I suppress the alpha index here. Okay, this is your inertia index. And this is in basis P. Now if I go to the basis A prime, I'm going to get exactly the same thing. what you can see is that if I go to the basis B prime, this should be there, because by definition this should be this. But what it tells me is that because my matrix has become diagonal, all these become 0. That means, please remember that I now summed up over all of this. So all I can get is, I'm just going to write this in the following way: alpha equal to 1 to m alpha. Let me just write this and then I will x2 prime alpha square plus x3 prime alpha square. And then I get the 0, 0 here, 0, 0 here. Then I get sigma alpha equal to 1 to m alpha, x1 alpha whole square plus x3 alpha whole square, 0, 0. And then I get here sigma alpha equal to 1 to So I'll put prime here because these are the coordinates of the value basis. x1 alpha square. So what you can see is that I just diagonalized it, and by looking at the form of this from here, I can say that this answer must be the same as this. Now you look at this, what is this? So this, if I go back again, so I'm in the prime basis. So this was my original basis. The prime basis is this, phi 1 cap, phi 2 cap, and I have to say phi 3 cap. And let us just take for one particle. Okay? So let's say I just take this, the diagonal element here. So I suppose I take for the first particle. So for the first particle, let us say the coordinates in this with respect to this phi 1 cap, phi 2 cap, phi 3 cap is x1 prime 1. So I'm just dropping the first index, so it's x2 prime and x3 prime. Right? Suppose the first particle is, or let's say the alpha. Okay, this is for the alpha particle. The position of the alpha particle. Now, see, I'm not changing the origin, but with respect to this new basis, x1 prime, x2 prime, x3 prime. I drop the alpha index there because comes in right now. Now, x2 prime and x3 prime, what are they with respect to this? So, if I see, in the sense that you have this axis phi 1, so if x1 prime is a coordinate along the phi 1 axis, x2 prime is the coordinate along the phi 2 axis, and x3 prime is the coordinate along the phi 3 axis. Now, if you look at this first, look at this term. This is like a look at for the alpha particle. It is simply m alpha times x2 prime alpha whole square plus x3 prime alpha whole square. What is this? What is x2 prime alpha square plus x3 prime alpha square? So think about, suppose this is your phi 1 axis. Now x2 prime will be this distance, because say suppose this is your phi 2 axis, and let us say this is my phi 3 axis. So x2 prime square is this, x3 prime square is this. So what will be x2 prime square plus x3 prime square? It's the perpendicular distance from the axis, from the phi 1 cap axis. Would you agree with that? The square of the perpendicular distance. This quantity is the square of the perpendicular distance from the phi 1 prime axis or from the phi 1 cap axis. Would you agree with that? So imagine that the particle is at x1 prime equal to 0. For simplicity, let's just imagine that it's exactly the x1 prime is 0. So that means this part is 0. But suppose it is at some distance along the y-axis or the phi 2 axis with some x2 prime, and along the z-axis or the phi 3 axis with x3 prime. So what is the perpendicular distance from the phi 1 axis?
x2 prime square plus x3 prime square.
x2 prime. The square of the perpendicular distance is x2 prime square plus So you have taken the perpendicular distance from the phi 1 axis multiplied with m. This is like mr square. And this is, I think, how you have defined your moment of inertia in your earlier, at least in school and say maybe early BSc. Is this familiar, the definition?
Yes.
That moment of inertia is defined like that. So you can see that when I go to the principal axis basis, or if I go to the frame or to the coordinate axis where I choose my principal axis as the coordinate axis, then what I will get back for the diagonal values are nothing but our usual familiar ideas of moment of inertia. That it is the mass times the square of the perpendicular distance of this particle from the axis along which I'm or axis along which I'm going. But see, this tells us something more now. We found that lambda 1, lambda 2, lambda 3 are real. But now you can see that lambda 1, lambda 2, lambda 3 must be equal to this kind of quantities. So my lambda 1 should be equal to, say, for example, if you look at this, alpha equal to 1, m alpha. Let me call this as, okay, so let's x2 alpha prime square plus x3 prime alpha whole square. Now this particular thing, for a particular alpha, what can this become anytime negative? Okay, this is a square of a distance. Can the square of a distance, can it become negative anytime?
No.
It cannot become negative. And so this part which is inside the square bracket cannot be negative. I'm multiplying with the mass. Mass is always positive. So you can see that in this summation, each term is always a positive quantity. It can, sometimes it can be 0, but it cannot ever become negative. So you can say therefore that lambda 1 can only be a positive quantity. It must be greater than or equal to 0. And the same arguments I can use for this. Because here you have x1 prime square plus x3 prime square. Here I have x1 prime square plus x2 prime square. So what you can see is that now I can say that my eigenvalues lambda I are not just real, but they are greater than or equal to 0. So this is something more I can see. So if you go back again to our angular momentum relation, so I have got this, in the new basis I have lambda I prime omega prime I. Or let's write this. A prime. I write it for lambda 1. Omega I prime. There's no summation over I here. Because of the fact that I have or if you like, I can write it in the column. Let's write it this. So whenever I write, I don't want any summation, then I explicitly write like this because this gives an idea that you're doing a summation, but I don't want to give you that idea. So this is no summation. So what this also tells me is that see, the fact that my lambda I is always greater than or equal to 0. So what it tells me is that depending upon the component of the frequency, this L prime will be always a positive quantity. If I take this to be the magnitude and if this is taken to be a positive quantity. So that is something more I can say. So again, to go back again to inertia tensor therefore. So therefore what you can see is what I tried to do was I tried to motivate for you now that if I give the more general, now if I take the most general form that I'm not saying that I am the principal axis basis, but say I have the usual form. Then the diagonal elements are known as the moments of inertia. And in the principal axis, if I choose the principal axis basis, if I choose a mutually perpendicular axis as my basis, in that case you will find that the dipole elements simply will correspond to the moments of inertia about the three different for the three mutually perpendicular axes, and we will get back our usual definition for the inertia. Yeah, and that's
नाही त्याच्यात आणखी सांगतो तुमच्याकडे काही ऑफिसमध्ये जर काही असेल तुमच्या ऑफिसला येऊन भेटलेलं तर बरोबर म्हणजे अगोदर तुम्ही एक्सप्लोरेट हे सांगू शकता कुठे कुठे जायचं नाही जायचं ओके काय करत सर नाही ऑफिसमध्ये जर आलो तुम्ही असं संभावना की टॉपिक
Now, let us just ask the question, what happens, suppose my eigenvalues, I assume that I had three distinct eigenvalues, so I said we were guaranteed from our theorem that I have three different or three mutually perpendicular axes. But suppose now that I don't have three distinct eigenvalues, let us say two of them are the same, then what happens? Can I still choose three distinct or three mutually perpendicular axes? Can I still find out three mutually perpendicular principal axes or not? So I will leave this as a question. So the exercise is that find out what happens. Is it possible for me to choose three mutually perpendicular axes in case that you don't have three distinct eigenvalues? So first take the case when lambda 1 is same, lambda 2 and lambda 3 are the same. That means two of them are the same. Then consider when all three are the same. Okay, and I think you should be able to work this out by using whatever you have learned in your vector spaces. So this is some kind of an application of that. So please do this. I'll continue on Wednesday. I have to stop. Very good.